I want to show you guys the classic proof that the harmonic series diverges. So we're not going to say this right here is a P series and the P is equal to 1, so it diverges. No. And we are not going to be using integral test either. This right here is the classic proof, so check this out. First, we are going to write down PF. Whenever you are doing a math proof, go ahead and write that down. This is super cool. And I'm actually going to put this down again right here. Here we have the series as n goes from 1 to infinity, and we have the 1 over n. And this means we're plugging 1, plugging 2, and so on, and then add up everybody. So we will have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And let me just write down a couple more of them. So let's say 1 over 7 here, and then 1 over 8, and then so on. Cool. Right here, we are saying that when you add up everybody, this is going to be approaching infinity. That's what it means to have a divergence in this case. So the result is not finite, but really? Why? Let's think about this a little bit. Because maybe you have seen my video on the infinite geometry series already. This is the famous one, so let me just put this down right here. Note, if today we only have 1 plus 1 over 2, and you see, so far so good. But I'm not going to put down the 1/3, I'm just going to add 1 over 4. And then next, I'm not going to add these, but I will just put down 1 over 8. And the next one, so you should notice that I'm just kind of like pick and choose, huh? The next one I will choose is 1 over 16, and then so on. The denominators, they are just the powers of 2's, right? Cool, but let me tell you, this right here actually converges to a nice number, 2, because 1 plus 1 is 2. So this right here actually gives us a finite value, but this is infinite. Pretty crazy. And the reason is because we have a lot more that we're adding than this. So that's pretty much the idea. Let's see what we can do with that. Okay. Maybe you guys noticed that purpose started at 8, which is 2 to the 3rd power. So let's actually focus on the 2's. Huh? Here we go. This is just 1, and this is just 1 over 2. That's okay. And then I'm going to put down 1 over 4 here, and I'm going to put down 1 over 8 here, and so on. If I write down more, the next one I will put down is 1 over 16. If I only have these, they will just be 2, but I do have others. Now, check this out. Here we have 1 over 3. If you compare 1 over 3 with 1 over 4, this right here is actually greater than 1 over 4, right? And we know that 1 over 4 plus 1 over 4 is 2 over 4, which is 1/2. What's the next number? So I'm going to replace the 1 over 3 with 1 over 4 here. But because I replaced it and this is bigger than that, so instead of putting down equal sign, we will have a greater than sign. And in fact, I will do the same thing for these numbers. Here we started at 1 over 8, but this number, 1 over 7, is greater than 1 over 8. And likewise, this right here also is greater than 1 over 8, and of course that is also greater than 1 over 8, and so on. Cool? Cool. Now, this is how you kind of read the inequality and also the equal sign in a mathematical proof. So we are saying that this right here is greater than this expression. But next, I'm going to put down equal sign because I'm going to show you this expression is equal to the next one. So we're not saying this is equal to that because there's a greater than in the middle. I got confused before when I first learned math proof, so I just want to point out that for you guys. So this is what we'll do. 1 is 1, 1/2 is 1/2, no problem so far. But if you look at 1 over 4 plus 1 over 4, that is 1/2. So I can just put down 1/2 right here. And again, this is equal to that. Next, aha! 4 over 8 is also 1 over 2. Let me just put that down. And in fact, this kind of grouping will work because the next one we can just go up to 1 over 16, which is power of 2. So you know that the next part is going to be, we have the 1 over 2. And the truth is, how many of these do we have? Infinitely many. So we can just keep adding 1 over 2 and so on, so on, so on. And this is super cool. Yeah, this is super cool. Yeah, because we are turning this into the sum of infinitely many 1 over 2. And of course, when we add up infinitely many 1 over 2s, this right here will give us past the infinity. Therefore, this right here diverges. And that's the classic proof. Very cool. And you might be wondering why this works, right? Why this converges to 2, not infinity. And the reason is because, as we said, we have a lot less numbers that we're adding. And in fact, this is a geometric series. To show this right here actually converges, this is my favorite cookie example. Imagine you just focus on this part, okay? Because 1 is just 1. But if you look at this part, let's say we have a piece of cookie in the square shape. If today you finish the cookie, then you are going to be sad because tomorrow there's no more. So what you should do is cut this into 2 pieces. Just eat half of it today and save the other half for tomorrow. So that way when tomorrow comes, don't eat the whole thing either. Tomorrow comes, you are going to cut this into 2 pieces and just eat half of that, which is half of half, which is going to be 1 over 4. And then the next day comes, you have this waiting for you. But again, we have to play smart. We will have to cut this into half again, and then just eat half of this, which is half of 1/4, which is 1 over 8. And then so on, so on, so on. So you guys can see, we can actually repeat this process forever. All right? And you see that this right here came from what? That one piece of cookie. Meaning that altogether this has to be equal to 1. So that's why I said 1 plus 1 is equal to 2 for that. But of course, this right here turns out to be 1 plus 1/2 plus infinitely many 1/2, and that's infinity. I think this is super cool.